If we take a look at question number one, it basically asks you to describe your understanding of two of the charging methods, the first being conduction, the second being induction. I've drawn some diagrams to make it a little bit easier to understand with regards to the specific questions, but overall I tried to get across the main points. So the first one asks how you would charge a neutral metal sphere with a positively charged metal sphere through conduction. There's really two things you have to make sure you explain or you understand about conduction. A lot of people just say it's charging through contact, but every charging method requires some kind of contact, so it's a little bit of a vague explanation. The most important thing to realize is the two objects must start with different charges. So in this case, you have a neutral and a positive sphere, so you therefore have the means to perform conduction. But if they don't have opposite charges, conduction is off the table. You have to take those two objects that have different charges and you have to allow them to make contact. And as long as they are conductors, they're made out of metal, something like that, the electrons will be able to move and flow from the less positive to the more positive option. So in this case, we have a neutral and a positive. We don't actually have any negative objects, but we do have a neutral which is less positive than the actual positive object. So electrons will jump from the neutral to the positive because they would prefer the more positive option. Then you kind of separate them, and you will find that, as we said, electrons from the neutral would have jumped to the positive. And the big secondary point you must include in your explanations is that they will end with the same charge, because electrons are moving to the more positive option. The only point at which electrons will stop moving is when there is no longer a more positive option. If these two at any point have different charges, electrons will continue to seek the more positive option. They will only stop once those two reach the same charge. So with conduction, you have to have two different charges prior to contact. After contact, both must end with the same charge because that is the only point at which electrons will have stopped moving between the two objects. The second method here is induction, and in this specific case, they'd like you to explain how to charge a neutral sphere using a negatively charged sphere through induction. Now, the important thing to recognize with induction is that that actually charged sphere can never make contact with anything else. If it does, you immediately will get conduction. So no contact can happen with that charged object. There's still contact, but not with the charged object. Contact with the differently charged object results in conduction. Here's how induction differs slightly. The first step is to take your charged object, which in this case is a negatively charged sphere, and bring it close but not touching your neutral sphere. That again needs to be a conductor. So you can only charge conductors through induction. As a result, the electrons will be repelled and they will get as far away as possible from this negatively charged sphere. This still has a neutral charge, 3 protons, 3 electrons. However, it is now polarized. The second step is to provide contact to that polarized sphere with some other conductor, usually a hand, it could be another metal sphere, it could be a copper wire, anything that allows electrons to move freely. In this case, because the electrons would like to be as far away, electrons will jump from the sphere into the hand and eventually to the body, because that allows them to get away from this negatively charged sphere to an even higher degree. They would like nothing more than to get as far away as possible. Once a pathway has been provided, they will take that chance. The third step is to remove that conductive pathway. So take the hand away, take the wire, the other sphere, whatever you like. Take that away. Once that contact is broken, electrons cannot transfer back and forth. Now, in this case, I've drawn this sphere with no electrons. Just be aware that that's impossible. There will still be some electrons on here. You won't lose all of them, but you will lose enough for the object to become positive. But I'm drawing these diagrams a little bit simplistically to get my point across. You will notice that at no point in any of these diagrams has the charged object gained or lost any electrons because no physical contact has been made. And then once you separate them far enough to avoid any kind of polarizing effect, the objects will end with the opposite charges. So to a certain extent, it's not directly the reverse, but in conduction, you have two objects initially with different charges, make contact, and then end with the same charge. In the case of induction, you have two differently charged objects that never make contact, and you end with the opposite charge. So you will always end up with the opposite charge in induction than whatever charged object you began with. A negatively charged sphere will produce a positively charged, and a positively charged sphere through the reverse process would produce a negative charge. For number 2, what method of charging is demonstrated when a polyester rod is rubbed against silk? Well, the keyword being rubbed implies that you're generating some friction between these two materials, and therefore this is charging by friction. In order to describe the charge on both the polyester rod and the silk, you need to take a look at the triboelectric series. So the triboelectric series will tell you about the affinity, the electron affinity of these materials, or how strongly they form bonds with electrons, how strongly they can rip them away from other objects. So here we're told that the polyester becomes negative and the silk becomes positive due to their higher and lower affinities for electrons respectively. And this was found out using the triboelectric series. I'm old and I forgot already. Polyester and silk. So if I go down and I look at my triboelectric series, polyester you will find here, and silk is up here. So silk is higher on the list, meaning it gives electrons easily. Polyester is lower on the list, which means that's cool, which means it takes electrons more easily. So the polyester will take the electrons from the silk, making the polyester negative and the silk positive. You can only use triboelectric series when you're analyzing charging by friction. It is useful for no other methods outside of charging by friction. The person then touches the silk at several different locations. It's important to point out that they had to touch it at several different locations because silk is an insulator. So just touching the silk at one corner will not redistribute the charges. You would have to take your hand and kind of rub it all over the silk because the electrons cannot travel from your hand to the silk in one touch. You'd have to touch different points so that they could jump off at each successive location. However, the question is really asking what happens in terms of electrons and protons. Hopefully you realize at this point that protons do not move, they will never move, so that's just kind of a trick question. Protons will not move at all. Electrons, when two objects with different charges are allowed to make contact, they will always choose to move to the more positive object. Since I have a neutral hand and a positively charged silk, that means that when they're allowed to contact, electrons will jump from the neutral to the positive because it is the more positive option. Therefore, electrons jump from the hand to the silk. This method of charging, this contact that was just described in part C, would be charging by conduction. And the reason we know this is the two objects made contact, but more importantly, they had different charges to begin with. That is charging by conduction. It will not be a huge zap because by touching an insulator such as silk, you won't have all these electrons be able to just flow on and spread out, but as you go and move your hand around it, you will wind up giving electrons to this object. So your hand becomes a little bit more positive, the silk becomes a little bit less positive, and you essentially wind up with a very low positive charge on both. Unless you don't have shoes on, then you can actually pull electrons up from the earth and you can ground everything. But the important thing to realize here is that both objects essentially end with the same charge, and the electrons will go from the more negative to the more positive option through the process known as conduction. It has everything to do with the fact that they had different charges prior to contact. Question number 3 tends to throw a lot of students off, partly because they overcomplicate it, partly because they might not feel like they fully understand how an electroscope works or what exactly it is. That being said, you don't need that information to actually answer this question. So the important thing is to understand that it states a charged rod is brought close to but not touching a neutral electroscope. So you're shown that this needle deflects different amounts. That could certainly throw some people off, but this is the most important piece of information to realize. If no contact is made, there's no pathway for electrons to transfer. So if I slide back up here, in order for conduction to occur, two differently charged objects must touch. In order for charging by friction, the rod must be rubbed against the silk. They must touch and be rubbed against one another. For induction, while you're not touching the charged object, you still need contact between two other objects. So it's important to realize that for any electrons to transfer in any charging method, you have to have some kind of contact. We're told here that these charged rods never make contact, therefore that eliminates conduction. Nothing in this problem tells me that any two materials are being rubbed against one another. That eliminates charging by friction. I don't have a third object that comes in and touches the electroscope as I did in this example, such as the hand. So if I don't have any of those touchings occurring, no contact, none of these charging methods could have occurred. So there is literally no charge on this electroscope. It remains neutral, so it has zero charge. Now that begs the question, how in the world or why is this needle actually moving then? And that comes down to the fact that these electroscopes are only polarized. So to explain that further, this kind of ring part is just the support, the stand, and this is the base so it doesn't fall over. The actual electroscope, the part we're concerned with, is this T-piece, which is made of metal, and this little metal needle, which is on a hinge here. So that's what we're concerned with, and I kind of showed down here in these 4 diagrams what's occurring inside each electroscope with each case. So in A and B, a positively charged rod is brought near the electroscope, and as a result, the electrons will travel or polarize towards the top to be as close as possible to this positively charged rod. The same thing occurs in situation B. That leaves the top of the electroscope with a locally negative charge and the bottom with a locally positive charge. Now, because the bottom has become positive, that means that the positive section here and the positive needle will repel one another, and the same occurs in B. Now, A repels slightly more, which probably denotes that this rod is a stronger positive charge than this rod, because it's able to suck up more electrons, which causes a bigger difference, and therefore a more repulsive positive charge down here. So while the same thing occurs in A and B, it's important to note that the reason the needle acts out has a lot to do with the fact that there's more polarization occurring here. In the case of C and D, it is just the reverse. You have a negatively charged rod, which is repelling those electrons down towards the base of the electroscope, leaving the top with a positive charge and the bottom with a negative charge. Again, this needle repels because all the electrons are down here, making this section negative, and the electrons are also down here. The difference in the degree to which that needle repels has to do with how many electrons are down there. So again, this is likely a much higher negative charge than this is. But in all cases, you are polarizing the electroscopes, but there is no contact, so no electrons can transfer. All electroscopes have a value of 0. When it comes to conductors and insulators, it's important to realize that conductors and insulators are words we use to describe the material, not the object itself. So a conductor is any material that allows electrons to freely move within that material. Things such as metals like gold, silver, copper, human body is a good conductor, salt water or natural water that has minerals that allows the electrons to jump from like the molecule of the minerals themselves. Insulators, materials that do not allow electrons to move freely. Cloth, rubber, plastic, wood, paper, silk, cotton, anything along those lines. Now, some people say that conductors are materials that allow electrons to transfer easily. While that is true, it's important to realize that it's the material that allows them to move freely. No transfer is technically required. I can polarize a conductor very well because the electrons can literally move to one side. I can't polarize insulators as well because they can't physically move to the other side. So yes, it's true that you get a bigger shock from a conductor because more of the electrons can move to your body. It doesn't mean that that transfer between objects is actually required for the definition of a conductor or an insulator. It has more to do with how easily electrons can move around or within that object, not necessarily how well they can transfer, though there is a connection between those two concepts. In the case of question 5, I'm going to try and give my reasoning with these little diagrams on the side. I'll explain why I added certain charges and why I eliminated certain charges. So in this case, we are told that object A has a negative charge and object A and B attract. Well, if A is negative, there are two things that will attract that. One is a positive and the other is a neutral. The negative will polarize that neutral object and show attraction, and a positive and a negative will obviously attract. B and C attract. Well, B has two options. If B is in fact positive, well, what would attract a positive? Either a negative or a neutral. So I must include a negative and a neutral just in case B is positive. But on the flip side, if I was wrong and B is actually neutral, well, there are two things that will attract a neutral. A negative, which I've already included, as well as a positive. So because I don't know which is which, to account for both, for the positive I must include a negative and a neutral, And for the neutral, I must include a negative and a positive. So I include all three. However, I'll explain in a second why I've eliminated neutral. But originally, I must include all three. I then move on and I see that objects C and D repel. Well, I can now eliminate neutral because a neutral object can never repel anything. It's incapable. So I have two options. If C is negative, well, D must be negative because that's the only thing that will repel. Alternatively, if C is positive, then D must be positive. So I have to include both. I am not stating that C could be negative and D could be positive. That's impossible. I'm just quite simply saying that there is an option in which C could be negative, an option in which C could be positive, and therefore there is also an option in which D could be negative or an option in which D could be positive. D and E repel, E and F repel. Since everything just continues to repel, the same logic applies. E is negative or positive, F is negative or positive. So if I translate this over, B is either positive or neutral. C, D, E, and F can all be negative or positive, so those are options for the remaining four options. When it comes to part B, we have A is positive is what we're given. A and B attract. What attracts a positive? A negative as well as a neutral. We're then told that B and C attract. Well, if B is negative, positive would attract, as would a neutral. But if B was neutral, there's two things that would attract: a positive, which I've already included, as well as a negative. So I have to leave all three of these things because these two apply to if it was a negative, and these two apply to if it was a neutral. I don't know which it is, so I have to leave all three. Now we come down here. Objects C and D attract. Well, if C is positive, it will be attracted to a negative or a neutral. If C is neutral, it will attract either a negative or a positive. And if C is negative, it will attract to a neutral or a positive. So I have to leave all three options because all three have at least one case where they could attract to C. And then I move on. D and E repel. Well, if D was neutral, it could not repel anything, so therefore I can eliminate neutral. That leaves D as positive or negative. And if D and E repel, that means E would be negative or positive. If E and F repel, again, negative or positive. So therefore, if I translate this over, B is negative or neutral. C could be anything. D, E, and F are either positive or negative. For number 4, I will explain the diagram quickly, and then I will explain how that got me my answers. But we are given two spheres, conducting spheres that are on insulating stands, so I don't have to worry about electrons being able to travel to the ground. And I bring a third sphere, sphere C, with a negative charge close to, but not touching sphere B. Well, as a result of this repulsion, the electrons in these objects, most of them will travel into A to get away from negatively charged sphere C. Since A gains the electrons from B, it becomes negative. And since B gives its electrons, some of its electrons to A, B becomes positive. Now it's important to realize that for every single electron that B lost, A gained. It would be like trying to give a friend $1 at a time. You give them $1, they gained $1, you lost. You give them $2, they gained 2, you lost 2. If you keep lending your friend money, it is impossible for them to gain more money than you lose because you're only transferring it between the two of you. Which is why for question C, the magnitude of both must be equal. Granted, they are equal and opposite. A is becoming more negative and B is becoming more positive as electrons transfer. But if A becomes negative 1 coulomb, B must have become positive 1. If A becomes negative 10 coulombs, B must become positive 10 coulombs. There's nowhere else for those electrons to go. Conservation of charge therefore states that whatever charge A gains in negativity, B must gain in positive. It's impossible for one to have more or less than the other because they are transferring electrons between one another. To explain what happens afterwards is we take the sphere B and we just slide it over so it makes contact with sphere C. Now we're breaking contact with A. There is no longer any pathway for electrons to enter or leave A, which means that A remains the same. The pathway is broken. There's no way electrons can enter or leave. So sphere A has its charge locked in. Once you remove sphere B, nothing can affect sphere A unless something comes along and touches it again, which has not occurred. When B touches C, you have two objects with different charges initially making contact. That tells you it's conduction. And in conduction, electrons will transfer from the more negative to the more positive option. So if sphere C is giving electrons to sphere C becomes more positive. Yes, it's giving its electrons away, which is why it becomes more positive, and B therefore becomes more negative. To look at the mathematics portion, we have to be very careful when we are determining what happens with the conservation of charge in these problems. You should also pay very close attention to whether you're being asked about a transfer of electrons or a possession of electrons. Transfer is how many were transferred between objects, the actual number that caused the change, and possess is how many you physically have. Imagine you had like $100 and you lent $10 to a friend. You now possess 90, but you transferred 10. So it's two different ways of looking at the same situation. So I'll show in a second why it's very careful to pay attention to that word. So here we're given that spheres A and B are brought into contact. As a result, how many coulombs of charge will be transferred between the spheres? They're not asking how much each will end with. They're saying how much will be transferred between the spheres. Now the first thing we need to do is figure out how much will they each end with, because I need the starting and the ending point to figure out how much of a transfer occurred. So I have -8 coulombs and -2. That gives me a total of -10 between those. Divided evenly among the two objects gives me a total of -5. So each of these spheres, when these two make contact, will end with a value of -5. That would be how many they actually possess, though. But I'm being asked how many are transferred. So I use sphere A as my example, although you can use either. Sphere A went from -8 to -3, which is a transfer of 3 coulombs. So I had 3 coulombs of charge transfer in order to bring my -8 coulomb to my -5 coulomb. You could look at the same for B. B went from -2 to -5, which is still a change of 3. It doesn't matter which one you look at. You just have to realize that transfer is the number that actually jump from one to the other, and possess is how many they actually have at the end. Going off of A, for part B, how many excess or how many extra electrons will sphere B possess after contact has been made? Well, we already know that they will each end with 5, but that's how many coulombs it will possess. If I want to convert that to how many electrons, I need to use our little equation. The number of electrons times the value of 1 will give me the total charge on the object. They're asking for how many, which is the number. The value of 1 electron, or the charge of 1 electron, is -1.6 times 10 to the -19th. And I've already determined that since they're asking about how many they possess, well, that's how many they end with, which in this case is -5. So if I just resolve this, I divide both sides by the elementary charge, I will find that 3.125 times 10 to the 19th electrons transfer. That's 31.25 billion electrons, which is an astronomically high number, but that's because -5 coulombs is like an extremely large lightning bolt. That's a crazy amount of charge. For C, we have to be very careful. We have to take into account that these two steps already occurred. We're not going back to the beginning. These two steps have already occurred, and each object A and B, currently have -5. They don't have -8 and 2. They've allowed to touch, and they now have -5 and -5 as determined up here. We're then going to let C, which has a charge of positive 19, make contact with these 3, and we will say, well, -5 for the first, plus -5 for the second, plus the 19 for the third gives me a total charge of positive 9, evenly distributed among 3 objects, gives me 3 coulombs. Now this is where I can stop because it's possessed. This is how much they each have, and I've given my answer in coulombs, which is what was asked of me. So they will each end with 3 coulombs of charge on each sphere. How many electrons will be transferred to or from A as a result of the interaction described up here? Well, we can't go back up to where -8 started. We have to look at the fact that it was at -5, and then after C comes over and makes contact, it goes from -5 to positive 3. So -5 to positive 3 is a transfer of 8 coulombs. I plug 8 as the total into my number of electron equation. And if I just solve this, the number of electrons that transferred is going to be 5.0 times 10 to the 19th electrons. Now, A went from -5 to positive 3. It became more positive, so it actually gave up electrons. So A lost 5.0 times 10 to the 19th electrons in order to become positive 3 from a -5. Question number 2 is a fairly straightforward Coulomb's law question. However, one of the charges were given in microcoulombs and the other charge were given in excess protons. So the first step is convert those excess protons into an actual charge. So we're given the number this time. So we know that there are 4.375 times 10 to the 13th more protons. So I'll use the value of 1 proton, which is just the positive version of the elementary charge. And when I multiply these two, I can get my total charge. Plugging this into my calculator gives me 0.000007 coulombs, which is also 7 microcoulombs, or 7 times 10 to the negative 6. Those are 3 ways to write that number. Once I know that this is 7 microcoulombs, and I was given that B has a 6 microcoulomb charge, now I can plug these values into Coulomb's law. So I have Coulomb's law written here. K is 8.99 times 10 to the ninth. I've plugged in the charge for A, which I determined here, the charge for B, which was given here, and the distance between them is 3 centimeters, which is 0.03 meters squared. Plugging all that in my calculator gives me 419.53 newtons. The fact that it comes out positive tells me it is a repulsive force. So I just look at A and say if B is repelling A will get repelled to the left. So that's why I've drawn a leftward directed arrow to represent the force of B acting on A. For C, I could certainly plug all the same numbers in and get the same value, or I could quite simply use Newton's third law. If B pushes A to the left with 419.53 newtons of force, the equal and opposite reaction would be that A pushes B with 419.53 newtons in the other direction. Equal in value, opposite in direction. For D, you have to make sure you're a little bit more careful with your algebra. But we're now told that they are moved to new locations, so I can no longer use 3 centimeters. But I'm told that at that specific distance, they experience an electric force of 11.24 newtons. Now, I made it a positive 11.24 because I know that both of these charges are positive. Two positives will repel one another, and in Coulomb's law, positive force means repulsive force. So I quite simply plugged in my force, my K value, my two charges, and I don't know the distance, so I left that as r squared. The first step would be to multiply both sides by r squared. So I wound up with 11.24 r squared equals k times q1 times q2. I then divide both sides by 11.24, and I get r squared equals kqq over my force. Now, plugging all this into your calculator should get you 0.0336, but that only equals r squared. Square root both sides, and you should find that the distance is 0.8 meters, or 18 centimeters. You have to be very careful with your algebra here. If you make any order of operations mistakes or anything along those lines, you will not get the right answer. It's worth practicing a few of these to make sure your algebra skills are solid. Question 3, we have multiple charges in a linear arrangement. The first question asks us to calculate the net electric force on charge B. It's important to realize that there is charge A nearby, which has an effect, and charge C nearby, which also has an effect. Now, Coulomb's law only has a space for two charges, so I have to calculate those effects separately. So first, I will find out what A does to B. So K, Q for A, Q for B. The distance between them in meters squared spits out 39.33 newtons. It is a positive force, meaning repulsive. So I say if A is repelling B, it will push B to the right, which is where this rightward directed arrow came from. I will then ignore A and say, well, if C and B are affecting one another, C is going to apply, well, K, Q for B, Q for C, divided by the distance between them in meters squared, and I get a negative 129.46 newtons. Now the negative just means attract, so if C is attracting B, that means C will pull B to the right. So I erase the negative and I replace that with a rightward directed arrow. I now know what A and C both do to B, and since they're both pushing in the same direction to the right, I simply add those two forces, and I get that the net force on B is 165.79 newtons directed to the right. I'm going to repeat this process for charge C, but I can save myself a bit of time if I use Newton's third law. So I've already calculated up here that C pulls on B with 129.46 newtons directed to the right. Well, if C pulls B with 129.46 to the right, then B pulls on C with the same amount of force, just in the opposite direction. So I can save myself some calculation time and just flip that direction around. Now, we calculated A on B, C on B. We have yet to look at how A affects C. We have not done that calculation, so I must now do that here. K, Q for A, which is 7, Q for C, which is negative 9, and the distance between them is 13 centimeters because it's 8 plus 5 centimeters away from one another. So divided by 0.13 squared gives me negative 33.51. The negative means attraction. Well, A is attracting B, which means A attracts C, so A will pull C to the left. So I will have 33.51, erase the negative, replace it with a leftward directed arrow. Both acting to the left means I add them, and I get a total net force on C of 162.97 newtons directed to the left. Finally, we can save ourselves a bit of time because these charges and distances are the same from the previous problem. So I could just steal the 39.33 and the 129.46 newtons. That's the force between A and B and C. That was just taken from BC and AB. The only difference is because they're not in a linear orientation, my directions may be different. A and B are positive, so they will repel, which is why A originally repelled B to the right based on the orientation. However, A is now above B, so it's not going to repel B to the right, it will repel B downward. Likewise, B and C are actually in the same exact arrangement, so C is going to attract B to the right, so this arrow stays the same. So the only difference really is that this is now directed down. I now have my vertical and horizontal vectors. I can combine them with right triangle geometry. There's two ways we can do this, but you have to follow what's known as the tail to tip method. So if I start with my downward arrow, my 39.33 goes down. I do not pick up my pencil from where I ended. I then go to the right with 129.46 newtons, and I can set up my right triangle. Alternatively, you could go left first and then down, and you'll notice that I get the same exact hypotenuse, same direction. However, I'm finding a slightly different angle. In either case, the hypotenuse, which is your net force, is found using Pythagorean theorem, a squared plus b squared equals c squared. So in either case, you should find that charge B experiences a net force of 135.3 newtons. And using the inverse tangent based on how you have this set up, you will either find 73.1 degrees. In this case, it's measured off of the vertical vector, which is the y-axis. So this would be 73.10 degrees off the y-axis. Alternatively, if you use this triangle, you would find 16.9 degrees off of the horizontal here, which is the x. So while you get the same hypotenuse and the same net force value, there are two angles which can be accepted depending on whether you're referencing the y or the x.